Welcome to Math, Week 5, Systems of Linear Equations in Two Variables. Today we will solve two-variable systems by substitution and elimination. We will classify the three possible outcomes, which are unique solution, no solution, or infinitely many solutions, and we will meet the 2 by 2 determinant as the numerical fingerprint of that classification. By the end, you will translate a two-equation system into matrix form and recognize where this same operation shows up inside linear regression. This video is sponsored by Subthesis. Visit subthesis.com to learn more. A system is two or more equations with the same variables true simultaneously. Solving a system means finding the variable values that satisfy all equations at once. Geometrically, you are finding where the lines intersect, and once we generalize, where planes or hyperplanes intersect. This week, we cover two algebraic methods, substitution and elimination. We will work through examples of both, then learn when to use which method. We will explore the three possible outcomes any linear system can have, and the 2 by 2 determinant, a single number that tells you which outcome you are in. Then we draw the line forward to linear algebra, matrix form, and to machine learning, the normal equation for linear regression. We also have a real-world application problem, a 10-question practice quiz, and a recap before previewing next week. The two algebraic methods you will use most are substitution and elimination. Both arrive at the same answer. The choice is purely about which is faster on the system in front of you. Elimination is faster when both equations are already in standard form, ax plus by equals c. You can scale and add immediately without isolating anything. Substitution is faster when one equation already solves for a single variable, like y equals 2x. Just plug in and you are down to one equation in one unknown. For the worked example coming up, we will use elimination because the two equations are already in standard form. But keep substitution in your back pocket. Half the quiz questions will use it. Now let us work through a full substitution example. We have the system y equals 2x and x plus y equals 9. Step 1. The first equation already isolates y, so substitution is the natural choice. Plug y equals 2x into the second equation to get x plus 2x equals 9. Step 2. Combine like terms. 3x equals 9, so x equals 3. Step 3. Back substitute into the first equation. Y equals 2 times 3, which gives us y equals 6. The solution is the point 3, 6. You can verify by plugging back into both equations. In the first equation, 6 equals 2 times 3. Check. In the second equation, 3 plus 6 equals 9. Check. Both equations are satisfied. Step 1. Choose a variable to eliminate. We will go after y. The y coefficients are 4 and -3, and their least common multiple is 12. We need the y coefficients to become plus 12 and minus 12, so they cancel when we add. Step 2. Scale each equation. Multiply equation 1 by 3 to get 9x plus 12y equals 30. Multiply equation 2 by 4 to get 8x minus 12y equals 4. Critical detail. When you multiply an equation by a constant, you must multiply every term, including the right-hand side constant. Forgetting to scale the constant is the most common mistake at this step. Step 3. Add the equations. The y terms cancel and we get 17x equals 34, so x equals 2. Step 4. Substitute back into either original equation. Using equation 1, 3 times 2 plus 4y equals 10, so 4y equals 4 and y equals 1. The solution is the point 2, 1. Always sanity check by plugging into the other equation. 2 times 2 minus 3 times 1 equals 4 minus 3 equals 1. Confirmed. So how do you decide which method to use? Here is a simple rule. Scan the equations first, then pick the cheaper path. Use substitution when one equation already isolates a variable. If you see y equals something or x equals something, substitution lets you plug in immediately and reduce to one equation in one unknown. It is also the better choice when a variable has a coefficient of 1, because isolating it requires no division. Use elimination when both equations are in standard form, ax plus by equals c. You can scale and add without rearranging anything. Elimination is especially efficient when the coefficients are already opposites, like plus 1 and minus 1, because you can add the equations directly with no scaling at all. The bottom line is that both methods produce the same answer. The only difference is how much arithmetic you have to do to get there. Always verify your solution by plugging it back into both original equations. This is the step most students skip, and it is the easiest way to catch arithmetic mistakes. Let us check our elimination answer, the point 2, 1. First equation, 3 times 2 plus 4 times 1. That gives us 6 plus 4, which equals 10. The right-hand side is 10. Check. Second equation, 2 times 2 minus 3 times 1. That gives us 4 minus 3, which equals 1. The right-hand side is 1. Check. Both equations are satisfied, so the point 2, 1 is confirmed as the correct solution. If either equation had not checked out, we would know there was an error somewhere in our work, and we would need to go back and find it. Make this a habit. It takes 30 seconds and can save you from losing full marks on an exam. Every two-variable linear system you will ever meet falls into exactly one of three buckets. Bucket 1, a unique solution. The two lines cross at one point. This is what most systems look like, and it is what we just saw with the point 2, 1. Bucket 2, no solution. The lines are parallel, same slope, different intercept, so they never meet. When you run elimination on such a system, you arrive at a contradiction like 0 equals 5. That contradiction is the algebra telling you no point satisfies both equations. Bucket 3, infinitely many solutions. The two equations describe the same line. One is a scalar multiple of the other. Every point on the line satisfies both equations. Elimination collapses to 0 equals 0, an identity that is always true but tells you nothing new. The solution set is the entire line. Let us look at these three outcomes visually. In the first case, one solution, the two lines cross at exactly one point. You can picture two lines on a graph meeting at a single dot. That dot is the ordered pair that satisfies both equations. In the second case, no solution, the two lines run in the same direction but never touch. They are parallel. No matter how far you extend them, they will never intersect. Algebraically, you see this when elimination produces a false statement like 0 equals 5. In the third case, infinitely many solutions, the two lines sit right on top of each other. They are the same line drawn twice. Every point along that line is a valid solution. Algebraically, elimination produces 0 equals 0, a true statement that gives no new information. The key geometric insight is that the number of solutions equals the number of intersection points. For a 2 by 2 matrix with entries AB on top and CD on the bottom, the determinant is A times D minus B times C. Diagonal product minus anti-diagonal product. That is it, one number. This single number tells you which of the three outcomes you are in. A 2 by 2 system has a unique solution exactly when AD minus BC is not equal to 0. If AD minus BC equals 0, the two equations are linearly dependent, either parallel with no solution or identical with infinitely many solutions. The same three-way classification from the previous slide now read off as a number. Quick check. The matrix from our worked example has entries 3, 4, 2, -3. The determinant is 3 times -3 minus 4 times 2, which equals -9 minus 8, which equals -17. Non-zero, so a unique solution exists. Here is a summary table connecting the determinant to everything we have covered. When the determinant is not 0, the lines intersect at exactly one point. The algebraic result is a unique ordered pair like x equals 2, y equals 1. The matrix is invertible, meaning you can solve the system using the inverse. When the determinant equals 0 and the system is inconsistent, the lines are parallel. The algebraic result is a contradiction, like 0 equals 5. There is no solution. When the determinant equals 0 and the system is consistent, the lines are identical. The algebraic result is an identity, like 0 equals 0. There are infinitely many solutions. The determinant is the single number that tells you which scenario you are in before you even finish solving. Solving a system of n equations in n unknowns is exactly the operation that matrix inversion performs. Write the system as A times x equals b, where A is the coefficient matrix, x is the vector of unknowns, and b is the vector of constants. The solution is x equals A inverse times b, provided A is invertible. Invertible is just the determinant test in disguise. For our 2 by 2 case, the inverse of A exists exactly when the determinant of A is not equal to 0, which is the same condition we wrote on the previous slide for unique solution exists. The bigger idea is that Gaussian elimination, the algorithm we will meet next week, generalizes the elimination method we just used by hand to systems of any size. The scaling and adding moves do not change. We just track them as row operations on a matrix. Let us see exactly how to extract the matrix form from a pair of equations. Take our elimination example. 3x plus 4y equals 10, and 2x minus 3y equals 1. The coefficient matrix A collects just the numbers in front of x and y. So A has 3, 4 in the first row, and 2, -3 in the second row. The unknown vector x holds x and y. The constant vector b holds the right-hand sides, 10 and 1. Now the original system reads A times x equals b, and if the determinant of A is non-zero, we can solve it as x equals A inverse times b. We already know the determinant is -17, which is non-zero, so the inverse exists and the solution is the point 2, 1, exactly what we found by elimination. This is the bridge between the algebra you do by hand and the matrix operations that computers perform at scale. The headline result of this lesson is that the closed-form solution to linear regression is a system of linear equations. The normal equation, beta equals the quantity x transpose x inverse times x transpose y, has the same skeleton as everything we have done today. The matrix x transpose x encodes the system. X transpose Y encodes the right-hand side. Beta is the vector of regression coefficients we are solving for. A numerical computing library's linear solve routine does this in one line, but conceptually it is the same operation as eliminating variables one at a time. Same elimination, same back substitution, just on a much bigger matrix. When you see a singular matrix error from such a routine, it means your system has no unique solution. The design matrix is rank deficient, equivalent to the no solution or infinitely many solutions cases we drew earlier. The determinant test we learned today is literally what numerical libraries check before they trust their answer. Now let us check your understanding with a short practice quiz. There are 10 questions covering everything from this lesson: substitution, elimination, the 3 outcomes classification, determinants, and the linear algebra and machine learning connections. Some are multiple choice, some are free response, and the last one is a reveal-style conceptual question. Pause after each prompt to think before I reveal the answer. Before the quiz, let us see how systems of equations show up in real life. Here is a movie night budget problem. You are buying snacks for a group. Adult tickets cost $1 each, and child tickets cost $C each. You know 2 facts. 3 adult tickets plus 2 child tickets cost $40. 1 adult ticket plus 4 child tickets cost $30. Using elimination, multiply the second equation by 3 to get 3a plus 12c equals 90. Subtract the first equation. 3a plus 2c equals 40, and the a terms cancel. 10c equals 50, so c equals $5. Back substitute into the second equation. A plus 4 times 5 equals 30, so a equals $10. Adult tickets cost $10 and child tickets cost $5. This is the same elimination technique we practiced, just applied to a practical scenario. Question 1. Solve by substitution. You have the system y equals 2x and x plus y equals 9. Take a moment to work through this before the answer. The answer is A, the point 3, 6. Substitute y equals 2x into the second equation. X plus 2x equals 9, so 3x equals 9 and x equals 3. Back substitute to get y equals 6. Watch out for the distractor 4, 5, which is the solve half trap, where students mix up the substitution direction. And 9, 0 incorrectly sets the wrong variable to 0. Question 2. Solve by elimination. You have the system x plus y equals 5 and x minus y equals 1. Pause and try this one. The answer is A, the point 3, 2. The y coefficients are already opposite, so add the equations directly. 2x equals 6, so x equals 3. Back substitute into the first equation. 3 plus y equals 5, so y equals 2. Watch out for the distractor 2, 3, which swaps the coordinates. Always write the answer in the order x, y, not whichever number you computed first. Question 3. If a system has parallel lines, the system has which of the following? 1 solution, no solution, infinitely many solutions, or 2 solutions? Think about what parallel means geometrically. The answer is B, no solution. Parallel lines have the same slope but different intercepts. They never meet. When you run elimination on a parallel line system, you arrive at a contradiction like 0 equals 5. The infinitely many distractor confuses parallel lines, which have no overlap, with coincident lines, which have full overlap. and two solutions is never an outcome for a linear system. It is always one, none, or infinite. Question 4. If two equations describe the same line, the system has which of the following? One solution, no solution, infinitely many solutions, or it cannot be determined. Think about what it means for every point on the line to satisfy both equations. The answer is C, infinitely many solutions. Same line means equation 2 is just a scalar multiple of equation 1. Every point on that line satisfies both equations, so the solution set is infinite. When you run elimination here, you arrive at 0 equals 0, an identity that is true for every x and y. The no solution distractor mixes up coincident lines with parallel lines. Question 5. Free response. Solve the system 3x plus y equals 7 and 2x minus y equals 3. Give your answer as an ordered pair. Pause and work through this one. The answer is the point 2, 1. The y coefficients are already plus 1 and minus 1, so add the equations. 5x equals 10, giving x equals 2. Back substitute into the first equation. 3 times 2 plus y equals 7, so y equals 1. A common mistake here is subtracting instead of adding when y coefficients are already opposite. Another trap is stopping at x equals 2 without finding y. A two-variable system needs both coordinates. Question 6. Free response. Solve the system 2x plus 3y equals 12 and x equals y plus 1. Give your answer as an ordered pair. Look at which method would be most efficient here. The answer is the point 3, 2. The second equation already isolates x, so substitution is the cheaper move. Plug x equals y plus 1 into the first equation. 2 times the quantity y plus 1 plus 3y equals 12. Distribute and combine. 2y plus 2 plus 3y equals 12, so 5y equals 10 and y equals 2. Then x equals y plus 1 equals 3. A common mistake is forgetting to distribute the 2 across the quantity y plus 1. Question 7. What is the determinant of the matrix with entries 3, 4 in the first row and 2, negative 3 in the second row? Just give the number. Remember the formula, diagonal product minus anti-diagonal product. The answer is negative 17. Apply the determinant formula directly. A equals 3, B equals 4, C equals 2, D equals negative 3. So the determinant equals A times D minus B times C, which is 3 times negative 3 minus 4 times 2. That gives negative 9 minus 8, which equals negative 17. Note that the determinant is non-zero, which means the corresponding system has a unique solution, exactly the case from our worked example. Question 8. Geometrically, the solution to a two-variable system is which of the following? The sum of lines, the intersection point or points, the slopes added together, or the y-intercepts averaged. Think about what solving a system means on a graph. The answer is B, intersection point or points. Solving a two-variable system geometrically means finding the point or points where the two lines cross. The other choices all conflate algebraic operations with geometric meaning. Adding slopes or averaging intercepts has no geometric link to the solution. The solution is always where the graphs meet. Question 9. Closed-form linear regression is essentially which of the following: random search, gradient descent, solving a large linear system, or bisection. Think about the normal equation and its structure. The answer is C, solving a large linear system. The normal equation, beta equals the quantity x transpose x inverse times x transpose y, has the same form as x equals A inverse B. Solving it is exactly solving a large linear system, the multivariable generalization of what you did this week. Random search and bisection are unrelated numerical methods. Gradient descent is an iterative alternative to the closed form, not the closed form itself. Question 10. Reflection. What does a zero determinant tell you about a 2x2 system? Take a moment to think about this before the answer. A zero determinant means the two equations are linearly dependent. Geometrically, the lines are either parallel, which gives no solution, or identical, which gives infinitely many solutions. Either way, you do not get a unique answer. The unique solution case strictly requires a non-zero determinant. This is also the boundary that numerical linear solve routines police. When the determinant is zero, or so small it rounds to zero, the routine raises a singular matrix error rather than dividing by zero. The determinant test we learned today is built into every linear algebra library. Quick recap. You solve two variable systems by substitution and elimination. You classified the three possible outcomes: one solution, none, or infinitely many, and you previewed how the 2x2 determinant encodes that classification numerically. Three trap families fell this week: the scale the constant trap, forgetting to multiply the right-hand side when scaling an equation; the wrong operation trap, adding when subtraction was needed because the coefficients had the same sign; and the half solution trap, stopping after solving for one variable. Each outcome supports later coursework. Substitution generalizes to back substitution in upper triangular form. Elimination generalizes to row reduction. Classification by determinant becomes the singular matrix test that protects numerical code from divide by zero failures. And closed-form linear regression is the same operation, scaled to many features. Coming up next. Next week scales to 3 variables and introduces matrices as the compact bookkeeping device. You will execute Gaussian elimination by hand on a 3-variable system, recognize the 3 legal row operations, swap, scale, and add a multiple, and meet the identity matrix as the multiplicative identity for matrix algebra. The pattern generalizes directly to the algorithm that every linear algebra library uses internally for solving systems of any size. See you next week. That wraps up week 5. You can now solve 2-variable systems by substitution and elimination, classify the 3 possible outcomes, and use the 2x2 determinant as the diagnostic that tells you which case you are in. If this helped, please like and subscribe. It tells the algorithm to put this in front of more learners. See you next week for 3-variable systems and your first matrices. Sponsored by Subthesis, subthesis.com.